Okay, so now I want to go through fetal circulation. So in a fetus in placental mammals gets its oxygen through the placenta. Placenta is up here in the mother. The placenta then attaches through the umbilical cord to the fetus. And there was a vein right here, which is the umbilical vein, was attached to our umbilical cord right there. Okay. Now what happens then is that this is fully oxygenated blood, because in the placenta then we get our oxygen exchange. So this is bright red blood. Blood that's fully oxygenated is bright red. Blood that doesn't have oxygen then is blue, right? That's why you get that black and blue coloration when you get a bruise, is because that's deoxygenated blood. As soon as you get a cut, right, when that blood hits the surface, oxygen hits it immediately and it turns bright red, so therefore you've never seen blue blood. So right here it comes in fully oxygenated, bright red. This then goes down through the liver. You can see it kind of bypasses right through the liver here in a shunt called the ductus venosus. So a vein that basically closes off upon birth, but before birth then it takes oxygenated blood and moves it down here into the bottom, being our posterior vena cava. So here we have bright red blood, here we have the vena cava. The vena cava then has blood that is just taken all of the blood from the lower torso. And so it's returning all of that blood from the lower half of the body to the heart, and it's fully deoxygenated blood. So here our red blood from our placenta comes in, mixes with our blue blood in our vena cava, and we get semi-oxygenated or kind of purplish red blood here. Now what happens then is our vena cava comes in and mixes, our posterior vena cava mixes with our anterior vena cava. Our anterior vena cava then has just drained everything from the head and the upper torso. So this then is fully deoxygenated blood. This is semi-oxygenated blood. It comes in here and becomes even less oxygenated, so even more purplish in color. That then comes into our atrium. Now I'm going to take a break and we'll talk about the heart before we go to the next step. Okay, so quickly we just want to go over the anatomy of the heart. I'm going to use my hand to do that, which is kind of strange, I know. But what I want you to do is take your left hand up, put it palm side in, take your middle finger over your index finger, this pinky up, ring finger down, thumb out. Okay, so this is your heart. It's also our Gem Bio greeting sign. You know, yay, hey, how's it going, dude? You know, it's nice to see you, my fellow Gen Bio Lab compatriot. It's also the heart. So here being our heart, then we have our anterior vena cava coming in here, our posterior vena cava coming in here. These then both come into our right atrium. They go down to our right ventricle and they go out our pulmonary artery. That then goes to the lungs, comes in our pulmonary vein, then our left atrium, our left ventricle, and out the aorta. Key thing on this is that our pulmonary artery then comes out the front with our aorta right behind it. Okay, so if you think about our heart, here's our pulmonary artery coming across the front of our heart with the aorta right behind it. So here's our heart, here's our pulmonary artery. Okay, so here is our vena cava coming in, our anterior vena cava here coming into the right atrium, semi-oxygenated blood. That goes down to the right ventricle. And all of that blood from the right ventricle then, in a typical adult heart, comes through the pulmonary. Okay, the pulmonary then usually is going to lead to the lungs. So we'll go here and we'll look, and we can see here that branch from the pulmonary right there into the lungs right here. Okay, but if we also look, and we'll go back here and we'll really grab these lungs and lift them up. All right, down here we can see then we have this vessel right here, and this vessel right here is leading down. So here's our pulmonary. It attaches to this, which is our aorta, dorsal aorta. If we look right behind the pulmonary, right, with our fingers, this is the aorta, this is the pulmonary. Here is our aorta, right behind the pulmonary. Pulmonary here, aorta here. Pulmonary attaches to the dorsal aorta right here. Okay, so this attachment behind this vessel going to the lungs, being our pulmonary artery, is the ductus arteriosus. Okay, so now all of this semi-oxygenated blood that goes in here goes into our pulmonary. Almost all of that then goes into our dorsal aorta, going down the body. That then ends up going down, and it goes to through our dorsal aorta, which comes down here, and then feeds into this umbilical artery and this umbilical artery. Okay, then that goes back to the placenta. So we have this movement of blood. Oxygenated blood comes in from the placenta, umbilical vein, ductus venosus, through the posterior vena cava, right atrium, right ventricle, into the pulmonary, back down the dorsal aorta, back up the umbilical arteries. Okay. The problem with that then is that we end up having the situation that, right, if almost all of our blood from here goes into here, very little blood goes into our lungs. Okay, and we don't really need a lot of blood in our lungs because they're just developing, right? We don't need the full complement of blood like we do in adults. That blood goes in the lungs. Very little blood comes back into this atrium right here. So the blood from our pulmonary vein comes back into this atrium, back into this ventricle. It goes out the aorta, and from the aorta then it goes up the brachiocephalic artery here and over to the left subclavian. So it fills the head. Very little blood actually goes in and fills the head with this ductus arteriosus intact. So how the heck are we going to get the blood to the head then, if this ductus arteriosus takes most of it down through the dorsal aorta? Okay, so there are two adaptations then. One is this ductus arteriosus. The second adaptation then is a hole in the heart between the right atrium and the left atrium. That hole in the heart is the foramen ovale, an oval hole, right? So when our right atrium pumps, half the blood goes down here, but half the blood goes over here. The blood that goes down here then, of course, goes out here through the ductus arteriosus and down. The blood that goes over here then goes into the ventricle, and it goes out the aorta and then goes up the brachiocephalic and over here. A couple things to note in here then is vessel color. So you see how all of these vessels are nice and blue because they've been injected with latex. You see how this one is nice and blue because it's been injected with latex, but this one is white. Okay. The reason it's white is because that wall is a lot thicker. And if we follow down our aorta, especially down here, our aorta is even whiter because this vessel is even bigger than that vessel. Okay. So one of those themes is conservation of energy, where we basically conserve energy by putting the energy into the walls of the vessels that we need to. Here we don't put much energy into these vessel walls because we don't need to. Here we put a lot of energy into these vessels because they're going to have a lot more pressure and are going to withstand that extra pressure. Likewise, when these pigs get injected, sometimes they inject it in the jugular. We have a tendency to have a lot more blue latex break in here because the same force in the jugular will break the vessels, whereas the same force in the umbilical artery down there will not break those vessels. So generally speaking, we have blue latex in fetal pigs, not red latex because of that. Okay, and so just as a quick review then, if we look at everything, right? We have three main adaptations here for fetal circulation. One is this ductus venosus. Two is this ductus arteriosus. Three is the foramen ovale. So upon birth, then the ductus venosus shunt closes off. The ductus arteriosus closes off. When our ductus arteriosus closes off, all of the blood then shoots through the pulmonary to the lungs. We have tons of blood coming in then from our pulmonary vein into our right atrium. That blood goes in, hits the foramen ovale, and the pressure then snaps shut the foramen ovale. Okay. When the foramen ovale shuts, then all of our blood from this atrium pumps down here, pumps over here, goes to the lungs, goes to here, goes to here, and then our blood goes out the brachiocephalic, the left subclavian, and down the dorsal aorta like it should. Okay. And then what happens then, of course, is that we end up getting fully oxygenated blood. So before we had semi-oxygenated blood in this whole system, the whole body was semi-oxygenated. Now we get fully oxygenated blood because what's coming into this atrium right here is fully oxygenated blood from the lungs. So this is all red blood. It goes here, all of the blood then going down and up to the upper torso, out to the capillaries is nice red blood, and thus that purplish color is going to disappear and is going to turn into more of a pinkish color because of the red blood cells then in there being fully oxygenated out to the capillaries. Okay. Now some problems happen, of course, in this situation, right? So let's say that we have a baby, and that baby stays blue, called blue baby syndrome. Okay, blue baby syndrome happens when the foramen ovale doesn't completely close. You end up having a hole in the heart so that some of the blood from here that's blue goes right over to here, mixes with this blood, making it kind of purplish. And thus that's what happens when you have a baby then that doesn't have the foramen ovale close all the way. So it stays blue. Doctors just give that baby oxygen. You get extra oxygen, then you have more oxygen in your blood, so it solves the problem. But then over the next couple of weeks, then that foramen ovale will close, right? People with holes in their heart, then that hole in the heart is sometimes caused by problems with that foramen ovale closing later in life. Okay. All of that then is just designed to bypass these lungs because we don't want all of our blood going to the lungs, and we want to save the energy then from going to the lungs and then just use that pulmonary circuit to get the blood from the placenta. Let's talk about one other thing since we're talking about babies and birth and what can happen upon birth, right? One of the interesting things is that here we have babies, right? A woman gets pregnant, she has a baby, she goes through a pretty painful labor then and the birthing process. Okay, so basically you're taking out the baby through a small opening. You know, I was always wondering why that would happen, right? Evolutionarily, you would think that, you know, if you were going to design this and make it really easy, you'd just have like this trap door where you could just snap open a trap door, open it, pull out the baby, then close it and let everything heal up and make it really simple. Why go through the whole process of taking that little, that whole baby through a small opening? You know, and sometimes labor, right, takes, 15 hours, 16 hours, so it's really very slow, laborious process. But one of the key reasons is that a baby's in amniotic fluid. It's in a fluid environment, and it basically has to get ready to go for a non-fluid environment. So these lungs then are totally filled with fluid. And really you have to get the lungs drained of fluid in order for the baby to start breathing. So what happens is that baby goes in, that baby's pinched super duper tightly, and then what you're part of the process is just taking these lungs, squeezing all of the fluid out of the lungs so that you then have, you don't have a problem with fluid in the lungs, right? Cesareans, of course, get around that, but you do have the potential problem with cesareans in that your baby does not have the lung capacity, you know, being totally dried out so that they can immediately go in and start breathing. What happens then to the baby is over the course of about 4 to 5 minutes, then the baby, a typical baby, starts purple, and then as all of these processes happen, the baby will turn normal coloration in about 4 to 5 minutes after birth. Okay, so I dissected the sheep heart so we can look inside. Foramen ovale is there, so we can see this blue latex going across that foramen ovale. One thing to pay attention to is typically the walls of the heart, so you can see how thick that wall is, see how thick that wall is. Usually in an adult heart, the left side is much thicker than the right side. Interestingly, because of the pressure, over here we actually have more pressure on this side, so this wall in a fetus is actually as big as this wall in the fetus. In the adult heart then, our left ventricle wall is way bigger than our right because of conservation of energy, because we don't really put in energy where it's not needed, and thus when we need the muscle we make it bigger, when we don't need the muscle it's smaller. Okay, so next we want to do the veins of the throat region. You don't have to know all of these, but we'll just start at the beginning. So right out of the top here is our right atrium. Right out of the top of that is our superior vena cava or anterior vena cava. Then basically the anterior vena cava drains the head and the shoulder regions. Head is cephala, shoulders and arm especially is brachial. So this is brachiocephalic. So right brachiocephalic, left brachiocephalic. Up here, these are pretty easy to get. Jugulars are very apparent. This is our internal side, so internal jugular, external jugular. Here's our cephalic vein branching off there. Down below that here, the first branch is our subclavian vein. Once our subscapular right there branches off, it turns into the axillary, and then at the next branch, it turns into the brachial up here. Okay, so now what I want to do is I want to show you the arteries of the neck region. Okay. So what I did was I took all of those veins, remember all those nice blue veins that were on top a minute ago? I took all of those out. Okay, and so typically if you want to see the arteries, well, you get rid of the veins. Underneath the veins then I have all the arteries. And so we can just quickly go through this. So here is our pulmonary artery, right behind the pulmonary artery is the aortic arch. That aortic arch has two branches off of it, one being the brachiocephalic, the other being the left subclavian. Our left subclavian then feeds the shoulder and the arm. It gives rise to the thyrocervical, and that gives rise then to our axillary. Our axillary then branches off into the brachial and feeds the arm up here. Now our left subclavian is here, but it's asymmetrical because our right subclavian is here. Our right subclavian again branches off into the thyrocervical and the axillary, then our axillary branches off into the brachial going into the arm. Up here then we have our common carotids. We have our right common carotid, we have our left common carotid. Okay, our left common carotid, then both our common carotids branch off into an internal and external carotid. Internal goes up to the brain, external feeds the neck and shoulder region. Okay, now people are different than pigs. In people, instead of having two branches, we actually have three. So we have a brachiocephalic, which gives rise to a subclavian, which then gives rise to a right common carotid, which then goes internal and external and feeds the brain. But we have a direct feed to our brain with our left. So we have a left common carotid, then which branches off and gives us a direct feed right to our brain being here. So we have brachiocephalic, left common carotid, and then left subclavian for us. Because we have that big brain, it gives us that extra blood going directly up to it. Okay, finally, just the last couple things. So our renals are easy to see. So here's a renal vein, here's a renal artery going into the kidney. Then down here, branching off of our dorsal aorta, then we can see our common iliac there, then we have our internal iliac and our external iliac that are easy to see.